the power of transistors and the challenges it faces. Computers are a collection of simplicity, and transistors are their basic element. Transistors operate like a switch, for which there are two possible states, on and off. This means that information in computers, and in general, in all electronic devices, is stored and processed with two symbols, 1 for on and 0 for off. The transistor revolutionized the electronics world because it enabled computers to perform complex operations in a remarkably small size and speed. This occurred because transistors were made of semiconductors. Unlike conductors and insulators that have a definite state, semiconductors can change their behavior in relation to their environment. They can rapidly switch from conducting and not conducting electricity. This enables the transistors to perform more changes on a switch at a time, and thus increase the amount of information that a computer can receive and process. To make computers increasingly more powerful, more transistors have to be packed into a chip, and to do this, transistors must become smaller. Today, we have gotten to the size of 14 nanometers, which is about the size of a virus. Yet at this phase, transistors will end up measuring just a few atoms, and at this minute size, things will behave very different than at a larger. But how do transistors behave in the first place? As mentioned before, transistors are made of semiconductors, but this is just the beginning of the story. For transistors to conduct electricity, the semiconductor from which it is made of must be manipulated. This process of manipulation is called doping, and it essentially consists in adding a foreign substance to a semiconductor, such as silicon, to increase its conductivity. To make a transistor, two different types of doping must be undertaken, P and N. With these new types of semiconductors, a transistor is formed. Together, these modified semiconductors will interact with each other, interchanging charges until no more are left to exchange. Exchange charges will stay between the two semiconductors, forming a barrier, known as a depletion layer, that will repel any extra charge that will want to move across the transistor. To turn the transistor on, a positive voltage has to be applied to build up enough energy that it can make charges, in this case electrons, to pass the depletion layer and ultimately conduct electricity. Essentially, we can control the transistor because of the existence of the depletion layer and the fact that we can apply positive charges to turn it on. But manufacturing transistors to about the size of a few atoms incites the electrons to behave atypically. By a process called quantum tunneling, electrons could get through the depletion layer without having a positive charge applied to the transistor. Producing transistors at this minute size means that we may lose control of computers. Data can get corrupted as it travels along the computer, or chips could get overheated to the point of melting. Although many of us do not need transistors to get so small in order to make videos or write reports or essays, to achieve the next big scientific and technological leap, computers need to get faster and smarter. Whether we choose to explore quantum, optical, or thermal computing, it is time to re-revolutionize the electronics world.